So last bit on vectors that we've got here, we are just going to do applications to mechanics. And actually, guys, the reason that I quite like this last bit here is because actually what we would have been doing after this is we would have had our first lesson on mechanics. After this lesson, obviously we're going to have the mock exams. And then after that, we're probably not going to spend much time going through the mock exams. I'll do a couple of videos of me doing the exams, and then you can look at those to be able to see how the exams went. I'll give them back to you, but I don't want to waste lesson time doing it. We will then be going on to mechanics. So it's actually quite nice that the last thing we're doing on Pure will like directly lead into what we're doing in mechanics next, because it just goes in really nicely. So I've got some things here, and actually I think I've made a mistake in this beginning bit. It says application to mechanics. Out of displacement, speed, acceleration, force, mass and time, all but mass and time are vectors. I think really we probably shouldn't have said the word speed there. We probably should have said velocity. Yeah, velocity is the vector word that we would use for speed. And we know that those things also have a direction. So displacement is the distance that something has moved in a particular direction. We've got some things, velocity, speed, obviously acceleration. Acceleration doesn't have a different word when it's a vector or a scalar, it just has the same word. And obviously a force could be a scalar, but it also could be a magnitude if we give it a direction. Mass and time can't be vectors. You obviously can't make mass and time have a direction. The reason I'm bringing this up again, because I've also done this with year 12, is now it's just that they can act in three-dimensional space instead. The whole theme of vectors so far has been 3D space. We remember, though, how we go from a vector to a scalar. What do we do to go from vector to scalar? We find the modulus of it, Pythagoras, we do the magnitude, lots and lots of different words that mean that. So if I want to just take the magnitude to find out what this force is, obviously we know, what do? We do
3 squared plus 4 squared plus 1 squared.
Yeah, 3 squared, 4 squared, 1 squared, which is...
Root 25.
Is it root 25?
Yeah, sorry, I meant to say.
It's root 26 newtons. Now, because this is now bridging into a mechanics topic, we probably wouldn't give the force as root 26. We would probably actually find out what root 26 is, which is 5.10 newtons to 3 significant figures. In mechanics, you should pretty much always give your answer to 2 or 3 significant figures. Very simply, we can see that this acceleration is just going to be the square root of 1 squared plus 1 squared, which is root 2, which is 1.41 meters per second squared. That's the sad life of a math teacher who knows the square root of 2. And displacement, we know, becomes distance. So I can then say that the distance is the square root of 12 squared plus 3 squared plus 4 squared. What is that without a calculator?
Which is 13.
Yeah, we can tell it's going to be 13 meters because the 3 and 4 will give us the 5, and then the 5 and the 12 will give us the 13. It's about knowing your Pythag triples there. Last of all, velocity, we'll change it to speed, and we'll get that that's the square root of 3 squared plus 4 squared, or 4 squared plus 3 squared, which is 5 meters per second. Literally nothing new here whatsoever, okay? The only thing that I would caution you about is whenever a mechanics question will say find the speed of something, you have to just make sure that at the end, you might have something that looks like this, and you might be like, oh, I've just done loads of work, and I've now got the velocity, that's done. But there are 2 extra marks that there are for the final part of that question. Not for the units necessarily, but those 2 extra marks that we have that are reserved are for doing the magnitude and then getting the final answer from there. So if it ever asks for the speed and you think, great, I've done all this hard work, I've got to that end point, you must make sure if it's asking for the speed that you take the magnitude of it and you have it from there, okay? We're going to just do a final example that will actually lead us into stuff. We'll probably do something very similar to this when we do mechanics. After the mock exams, we'll be doing some stuff like this in the future. This time we have got a particle of mass, 0.5 kilograms, is acted on by 3 forces. You'll notice that these 3 forces are acting in 3 dimensions. So I suppose the way that you'd probably imagine this is maybe like a tennis ball, and there are 3 people sort of like pulling on the tennis ball at different angles, or maybe you can imagine a tennis ball with 3 strings coming out of it, and they're all pulling it in different directions. And we're trying to work out overall what will happen to this tennis ball, which direction will it move in. So I've got these 3 forces here. The first thing that it wants me to do is to find the resultant force R. And I'm going to underline that because we're talking about it as vectors here. What does the resultant vector, how do we normally find resultants of two vectors? You add them together. Yeah, just a quick reminder. If you had the vector A and the vector B, the resultant vector is when you add them together. And this idea of resultant, you hear that word in mechanics when we talk about resultant forces. Okay, it's to do with like adding forces together when they're in vector form. So our resultant force will very simply just be F1 plus F2 plus F3. Take note of the way that I'm underlining the F's because they're all vectors. And really quickly, I'm just going to change these from IJK to IJK to IJK, which will be minus 1, 3, minus 3. This is where I often make the mistake writing it down wrong. And then we'll just add all those things together and see what they come up as. What does that come up as for the first one? 5.
Minus 1. Minus 3.
Minus 3. And when it's saying the resultant force here, I'm not clear whether it wants the magnitude or the resultant as a vector. But if I had to settle on one of them, I know which one I think I would settle on. Anyone got any ideas of what they think the question wants? Yeah, I think it's probably, because they've called these forces. When they're calling this one a resultant force, it kind of implies that they're talking about it in the language of vectors, which makes me think this is probably what the force would be. You also said like in the language of the question, and they've put theirs in IJ and K form. So if I was trying to be like extra careful, I might write 5I minus J minus 3K. So overall, these three strings are going to be dragging it over in this kind of direction. What were you going to say, Luke?
To be safe, would you do like the speed and the velocity and like would put that or that?
You mean like the scalar and the vector? You could do, but I don't think they've necessarily asked for them. If you wanted to, you could say, note the magnitude is, and then just do a quick bit on that as well. Yeah, if you wanted to. But I kind of agree with what Shahad said, that this makes sense that they're talking about it in IJ and K form, so it makes sense that's what they're saying. Part B, find the acceleration of the particle, giving your answer in a vector form. Well, how do we normally find acceleration when we know about forces? F equals ma. Well, surprise, here's a brand new formula for you. Oh, it's the vector form of it. Okay. So this F here is obviously referring to the resultant one. So I'm going to put it back in its column form, which is 5 minus 1 minus 3. The mass is 0.5. I could write that the acceleration, I could write x, y, z if I wanted to, or I could just write acceleration with it underlined. What do I need to do to both sides? Times it by 2. So I get 10 minus 2 minus 6 is the acceleration, but they wanted it in IJK form. So that's 10I minus 2j minus 6k, bracket it, add some units, and we've got what the acceleration is. Part C, pretty easy. We want to find the magnitude of the acceleration. Again, there's nothing new here, so I'm going to do the magnitude of the acceleration, which is just the square root of 10 squared plus 2 squared plus 6 squared, which is root 140. But because this is mechanics, I probably don't want to leave it as root 140. I want to change it to a decimal, which is 11.8 meters per second squared. Last thing that it says, given that the particle starts at rest, find the distance travelled by the particle in the first 6 seconds of its motion. So it's just SUVAT, okay? What you'll learn eventually is you can do SUVAT with vectors, but not all of the equations work with it. So remember that. I think that's probably the last topic we do in mechanics, that you can change the SUVAT formulae, most of them, into vector form. And you could find out, instead of the distance travelled, you could find out its displacement, and you'd have like the direction of where it's gone. So we're going to do SUVAT. We've said it starts from rest. We know that its acceleration is root 140. So I'm going to keep it as that exact form. What else do I need to know? T equals 6. And I want to find out what S is equal to. S equals ut plus a half at squared. So that is a half times root 140, because this bit's gone, times 6 squared. And we get 213 meters to 3 significant figures. That's it. And that finishes off nicely with the bits of pure that I'll be doing. I was going to say to look at exercise 12D, but I tell you what, it's so straightforward. It's not worth it. We'll be coming back around to these things when we're looking at mechanics later on. Okay?